Hi, everyone. My name is Michel Barbeau. I am from Carleton University in Canada. And the title of my talk is Frame Design for Adaptability in Long-Range Underwater Communication. And this is joint work with Stephane Blouin from Defense Research and Development Canada and Ahmad Traboulsi from Carleton University. This is the outline of my talk. I will first review the motivation behind this work. We have been working for a few years on the design of a communication system for the underwater environment. And I'm going to present today new features. I will discuss some performance results, and I will present 3 adaptability protocols. And at the end, I will summarize the talk. Motivation for this work. Global warming makes currently accessible large body of water in the Arctic. So it opens paths for maritime traffic. And this motivates the need for underwater communications that are required by several applications, such as in the field of defense, search and rescue, emergency response, and environmental monitoring. And our work focuses on the Canadian Arctic. What is specific about the Canadian Arctic? It's a cold and hostile environment. We have ice, we have noise, we have cold water, and we have deep and large bodies of water. So for a few years, we have been working on an adaptable long-range underwater acoustic communications. The last sentence highlights something very important. In the underwater environment, electromagnetic waves don't propagate very well. So the only viable solution is to use acoustic waves in the underwater environment. So it means we use sound. So we have a 2-layer protocol, physical and frame layers. I'll say a few words about the physical layer first. So one of the constraints that we have, we operate at very low frequencies, and this makes possible long-distance propagation. Now at low frequency, we have very narrow half-power bandwidth. So it means the signal must be very narrow bandwidth. Actually, ours is only 4.4 Hertz. We use 4-tone FSK. So it means each symbol contains 2 bits. So in each symbol, there is a synchronization bit and there is a code bit. So it goes from minus 2.2 Hertz to 2.2 Hertz in the baseband signal. And there is a difference of 1.46 Hertz between each symbol. So it's very narrow if you compare that to Wi-Fi or 5G signals with bandwidth in the order of megahertz, only 4.4 Hertz here. So building on the physical layer, we have a frame layer, so we can send data in data units called frames. Each frame is 162 symbols. Among these 162 symbols, there are 162 synchronization bits and 162 code bits. Within these 162 code bits, there are only 50 data bits encoded using convolutional forward error correction. Now, very recently, we have designed, building on this frame format, we have defined 6 modes of communication. And they are listed here in this table in the first column. So it goes from the 1 minute to the 20 minute. And you will soon understand why we call them 1 to 20 minutes. Second column, we have the symbol interval. Third column, we have the frame length in seconds. And fourth column, we have the effective data rate in bit per second. So if I take the first line, for example, the 1 minute mode, each symbol is 0.34 seconds. Okay, almost just slightly above a second. The frame duration is 55.3 seconds. So it takes almost 1 minute to send 162 symbols at that embed 50 data bits. So actually the data rate is just slightly less than 1 bit per second, 0.9 bit per second. And it goes like that from the 1 minute to the 20 minute mode. You can see at the end for the 20 minute mode, so a frame takes almost 20 minutes to send, and the data rate is effective data rate is very small, 0.05 bit per second. So it means data rate is very slow, but as we increase the duration of frame, we also increase the symbol interval. So it means if we maintain the same power level, we increase the energy in every symbol. So as we go from one mode to another, we go from a more robust mode, but at the same time, a less efficient mode. More robust means we can operate in more difficult conditions, like, for instance, weaker signal or higher noise, so worse signal to noise ratio. Okay, these are simulation results that we have obtained in the Matlab environment for each of the 6 modes. So we have a diagram here where the x-axis represents the SNR in a dB scale using a 6 kilohertz reference bandwidth. The reference bandwidth is very important when you calculate the SNR. On the y-axis, we have the FER, frame error rate, from 0% to 100%. So in this scenario, a frame is considered to be in error when at least 1 data bit is incorrect. So to count as a valid frame, the frame must be received perfectly. Okay, so in each of the 6 cases, we observe something that is very common when forward error correction is used, in particular convolutional. We have the waterfall behavior. So if I focus on the 20-minute mode, for instance, okay, so we have 100% frame error rate until we reach a threshold, a SNR threshold, which is slightly below minus 30 dB. And so suddenly the frame error rate improves, reaches 0%, and the protocol operates normally. Okay? And when we go from a longer in time mode to a shorter one, okay, so the threshold increases. So it means that we need a better SNR. But at the same time, we increase the efficiency, as I discussed before. Like if we compare for instance, the 2-minute mode with the 20-minute mode, we have about a difference of 10 dB in the threshold. And this is expected because in the 20-minute mode, the symbol interval is 10 times what we have in the 2-minute mode. Similarly, when we compare, for instance, the 1 minute and the 2 minute mode, we have a difference of maybe 3 dB in the threshold, and simply because we double the energy in each symbol in the 2 minute mode with respect to the 1 minute mode. So in addition to simulation, we have done several sea trials. One of the most recent sea trials that we did was in the Canadian Arctic in the summer 2019. Actually, it was done in a place called the Barbeau Strait. So it's an icy area, noisy because there is some maritime traffic. Ice cracking also creates noise, and wind that generate winds that generate waves. So it's a very harsh and difficult environment. Despite that, we have been able to achieve quite good results for the 2 minute mode. So on the right, we have a graph that plots the range as in meters, and the y-axis plots the bit SNR, and each point in color represents a frame that has been successfully received. And we have been able to demonstrate that we can communicate effectively across distances slightly above 30 kilometers. So we were quite happy with the results. Okay, a few words now about adaptability. So building on these 6 modes of communication, we can design adaptable condition. We need adaptability because in such an environment, the conditions can change rapidly due to currents or weather or time of the year or maritime traffic. Now, these are just few examples. Okay, so the first protocol, it's called half-duplex feedback. There are 2 parties, an initiator and a responder. In this diagram, we have the behavior of the initiator and the responder as a function of time. So in the half-duplex protocol, the initiator sends every frame one by one in each of the 6 modes, from the less robust but most efficient to the most robust but less efficient. So it sends the first frame in 1 minute mode, pause for the duration of a frame in the 1 minute mode. Send a frame in the 2 minute mode and pause for the duration of a frame in the 2 minute mode. Send a frame in the 4 minute mode and pause for duration of a frame in the 4 minute mode. In this scenario, the 4 minute mode turns out to be the one working. So the responder acknowledges with a frame in the same format during the pause of the initiator. And after that, they can carry on the dialogue in the 4 minute mode in the selected frame format. The 2 other examples that I'm going to picture, they are also based on a scenario where the 4 minute mode is the one that is working best. Okay, we have the second adaptability protocol. It's called full duplex feedback. Again, on the x-axis, we have time. On the y-axis, we have the initiator and the responder. The initiator sends, again, the frames in sequence from the less but most efficient, less robust to most efficient, from the most robust to the less efficient mode. 1, 2, 4 modes in this case. And the difference with the previous scenario is that the pause is very short between frames. So the responder can respond in parallel. So the initiator sends a frame in the 4 minute mode, no reply. 2 minute mode, no reply. And 4 minute mode, And the mode works, and the responder confirms by a frame in the same mode. And they can continue communicate the dialogue communicating in parallel, for instance, on two different frequencies. And the mode has been chosen. Again, this handshake can be repeated on a periodic basis to make sure that it's the most it's the mode that fits the conditions. Okay, the third adaptability protocol. Again, we have an initiator and a responder. The x-axis represents time. The big difference here is that the initiator uses more bandwidth, if possible, and it sends the 6 frames in parallel. So it starts at time t0, and all modes are sent in parallel. And the one that works, that is the one that, and the frame format that is the first to work will be acknowledged by the responder. So in this case, we have the 1, 2, and the 4-minute mode turns out to be the one that is working. So the responder acknowledges with a frame in the same format, and they carry on the dialogue in the selected format. Again, on a periodic basis, they can repeat this handshake to adapt. Okay, so all these things that I've discussed today have been implemented in a tool that works in the Matlab environment. This is how the interface of the tool works. There is a transmitter block and a receiver area. So the transmitter, for instance, we can select the frequency, and we can generate frames. And there are 2 modes of operations. Frames can be generated offline and stored in a file for future playback. It's very useful for simulation, for instance, and we can use noise to the frames. Or the frames can be played in real time. So in that case, the transmitter is connected to an audio interface. Similarly, from the receiver, we can decode frames in the playback mode, or we can also read the frames from the file, or we can also decode frames in real time. So in that case, the receiver is connected to an audio interface on the computer. So the URL to access this code on our GitHub page is cited in the paper. Okay, so I'm going to summarize the work here. So we designed 6-frame format for underwater acoustics communication. And we, together with that, building on these 6-frame, we define 3 adaptability protocols. We have simulation results that are published in this paper, and they confirm that robustness increase as we go from one format to another, from one when we increase the frame duration. At the same time, we increase the symbol duration and the energy in each symbol. In addition to simulation, we have done a few C trials. I discussed the one that we did in the Canadian Arctic for the 2-minute mode. Last summer, we tested the 1-minute mode in the Groenland area, and we are currently working on the analysis of the results, and they will be published in an upcoming paper. I thank you for your attention, and I welcome your questions.